Hello friends, welcome to my lecture on methods for finding particular integral for second order linear differential equations with constant coefficients. On this topic there will be 3 lectures. This is my first lecture on this topic. Let us consider the second order differential equation y double dash plus a y dash plus b y equal to Rx. Here a and b are constants and Rx is any function of x. So, it is a second order linear differential equation with constant coefficients. Now, we have already discussed how to find the general solution of the associated homogeneous linear differential equation, that is y double dash plus a y dash plus b y equal to 0. Now, we are going to consider or we are going to find the a particular solution of this non-homogeneous equation which is known as the particular integral. And we have already seen that once the general solution of the associated homogeneous linear differential equation is known and a particular solution of the non-homogeneous equation is known, then their sum gives us the general solution of the non-homogeneous linear differential equation of second order. So, this equation of second order can be written in a simple form by using the differential operator d. D is the differential operator d over dx. So, what do we mean by d? What do we mean by an operator? An operator t is a transformation from a space of functions v into the other space of functions w. These are vector spaces that transforms a function f in b to another function tv in w. Let us say b1 is the set of all differentiable functions f on I is any subset, I is any interval subset of R, and d with the differential operator defined on b1. Then df at x means the derivative of f with respect to x. We also denote it by f dash. For example, if you take f(x) equal to x to the power n, then d of xn, that is the derivative of x to the power n with respect to x, is n times x to the power n minus 1. Similarly, derivative of cos x with respect to x is minus sin x, etc. Since d is a linear operator, we can see that for example, if you can see here d is an operator from b into w. Whenever you take any two functions f and g in b, since b is a vector space and t is a linear operator, daf plus bg becomes a df plus b dg, where fg belongs to b1 and ab are constants. If f is a twice differentiable function on I, we write d df as d of f dash, or we can write it as df dash over dx, which is same as f double dash as f double dash x. The f double dash s means d square f over dx square. We write d df as d square f also. So, this way we can define higher order derivatives of f with respect to x. Now, the given equation then y double dash plus a times y dash x plus b times by x equal to Rx can be written in a simpler form as d square by plus a times dy plus b times by equal to Rx, or we can write it as d square plus ad plus b operating on y equal to Rx. Now, let us say let fd, if you take fd equal to d square plus ad plus b, then you can write it as fdy equal to, so fd is an operator which when x on y gives you d square y plus ady plus by. Now, let us see then the particular integral, which we also denote by pi, particular integral b in short we also write as pi, and we have the notation that we have taken for the particular integral is by px. So, by px is given by 1 over fd operating on Rx. Now, let us see how we get this form of the particular integral. by 1 over fd we mean that it is the inverse of the operation that is defined by fd. That is to say, if you operate by 1 over fd on this equation, let us say, then when we operate on the equation 1 by 1 over fd, then since 1 over fd defines an operation which is inverse to the operation defined by fd, we get the left hand side equal to y, and which is equal to 1 over fd Rx. Okay. Since by p is solution of the by p is a particular solution of the differential equation fd by p, I can write it fd by p. Okay. So fd by p equal to this, and so by p equal to 1 over fd Rx. We have assumed that by px is a particular solution of the non-homogeneous equation. So fd by p will be equal to Rx, and when we operate on that equation by the inverse operator 1 over fd, then what do we get is by p equal to 1 over fd Rx. So by px, the expression for by px is given by 1 over fd Rx. Now we can see that this fd can be broken into factors which are d minus m1 in d minus m2, and m1 m2 are the roots of the equation am plus m square plus am plus b equal to 0. See, in this equation let us write the auxiliary equation. The auxiliary equation for the given differential equation is m square plus am plus b equal to 0. Let us say the roots of this equation are be m1 and m2. Then m square plus am plus b is equal to m minus m1 into m minus m2. We can write it as m minus m1 and m minus m2. Now, so then what we will have, if you calculate this, m square minus m times m1 plus m2 and then plus m1 m2. So cutting the coefficients of the various powers of m both sides, we get m1 plus m2 equal to minus a and m1 m2 equal to b. Now fd is, we are writing as d minus m1 into d minus m2. So d minus m1 into d minus f2, if we can operate d minus m1 on d, that gives you m2 is a constant, we can write it as m2 times d minus m1. So this gives you d square minus m1 plus m2 into d plus m1 m2. Now making use of m1 plus m2 equal to minus a and m1 m2 equal to b, what do we get is which is nothing but fd. So fd can be written also as d minus m1 d minus m2. We can write d minus m2 into d minus m1 also, because that will also give the same thing. So order of factors here is immaterial, we can write them in any order. Now, so when we want to find the particular integral by px, we can write 1 over fd as 1 over d minus m1 Now what we do is we first operate on Rx by the operator 1 over d minus m2, and then whatever is the result of that operation, we operate on that result by the operator 1 over d minus m1. As I said in my as I just said, this can also be written as, the order of factors here is immaterial. So we can again we can also operate by 1 over d minus m1 on Rx, and then whatever is the result of that operation, we can operate on that by the operator 1 over d minus m2 to get the particular integral. In what manner we will have to operate by these operators on Rx depends on the function Rx, which we shall see when we solve some problems on this. Now, so this is one way of finding particular integral by Px, where we operate by the operators 1 over d minus m1 and 1 over d minus m2. Now there is another method by which we can find the particular integral. We can resolve 1 over fd into partial fractions. So 1 over fd is, if it is resolved into partial fractions, we have 1 over fd as one over fd is resolved into partial fractions as n1 over d minus m1 and plus n2 over d minus m2. So that 1 over fd operates on Rx. We have the operators n1 over d minus m1 operating on Rx plus n2 over d minus m2 operating on Rx. Now we can see the following. I mean, see, if you look at this expression, to find 1 over fd Rx, you have to operate on Rx by the operator 1 over d minus m1, and then whatever is the result of that, you have to multiply that by the constant n1. Similarly here, when you want to find this function of x, you have to operate on Rx by the operator 1 over d minus m2, and then whatever is the result, then you have to multiply that by n2. So here what we are doing is we are operating on Rx by an operator of the kind 1 over d minus alpha, where alpha is a constant. In the previous method, here also if you apply this method to find the particular integral, we are operating on Rx by 1 over d minus m2 or 1 over d minus m1, and then we operate by the other operator of the same kind on Rx, on the result of the operation which we get by operating on Rx by one of the operators. So when we operate by 1 over r d minus m2 on Rx, whatever function we get, we operate on that by 1 over d minus m1. So here also we are operating on Rx by an operator of the kind 1 over d minus alpha. So in both the methods, what we are doing, we are, in order to find the particular integral, we are operating by an operator of the kind 1 over d minus alpha on Rx. So let us see how we get when we operate on Rx by an operator of the kind 1 over d minus alpha, what function of x we get. Let us see, let us find this. So let us say that let 1 over d minus alpha, when operates on Rx, you get a function of x, say ux. So ux equal to 1 over d minus alpha Rx. We get a function, say ux. Alright, u is a function of x. Now let us operate on this equation by d minus alpha on both sides. So d minus alpha when we operate by d minus alpha on this equation, since d minus alpha and 1 over d minus alpha are inverse to each other, okay, we will get Rx equal to d minus alpha u. Now since d is d over dx, so we get du by dx minus alpha u. So what we get is du by dx minus alpha u equal to Rx, which is a linear differential equation of the first order with constant coefficient. Alpha is a constant, and we know how to find the solution of this differential equation. Du by dx minus alpha u equal to Rx. We find the integrating factor of this equation. So integrating factor is e to the power integral minus alpha dx, which is equal to e to the power minus alpha x. Then we know that when we multiply this equation by the integrating factor e to the power minus alpha x, the left hand side becomes an exact equation. So e to the power minus alpha x into u d over dx of that is equal to e to the power minus alpha x into Rx. After multiplying by the integrating factor, the left hand side becomes d over dx of e to the power minus alpha x into u, which gives, now let us integrate this equation with respect to x. So this gives u e to the power minus alpha x into u equal to integral e to the power minus alpha x into Rx dx. E to the power minus alpha x is never 0, so we can write it further as I am not writing a constant of integration here because the particular integral is free from arbitrary constants. So 1 over d minus alpha when f acts on Rx, the function u that we get is given by this formula e to the power alpha x integral e to the power minus alpha x into Rx dx. Now let us say, for example, let us see a second order differential equation with constant coefficient and see how we can find the particular integral. Okay, so d square by over dx square plus n square by, so the auxiliary equation is m square plus n square equal to 0, which gives us the complex roots m equal to plus minus in, and so the complementary function by Cx is given by a cos nx plus b sin nx. Now let us find the particular integral here. So particular integral by px, this is equal to 1 over d square plus n square, because the differential equation, given differential equation can be written as d square plus n square operating on y equal to sec nx. So 1 over d square plus fd is d square plus n square, so 1 over d square plus n square sec nx. Okay, now let us write the function fd in terms of its factors, 1 over d minus in d plus in. Now as I said, we can then find the result of the operation of 1 over d plus in on sec nx first, or the result of the operation of operating by 1 over d minus in on sec nx first, okay, and then we can on the result of which we get, on that we can operate by the other thing. Now here we can also break it into partial fractions. Let us suppose we wish to break it into partial fractions, then we will write it as one over d minus in minus 1 over d plus in divided by 2 in. That gives us 1 over d minus in into d plus in. Now let us apply this formula. this is nothing but 1 over d minus alpha operating on Rx. Okay. So, let us make use of this formula. So, let us find, first we find one over d minus In operating on sec nx. So, alpha is In here. So, e to the power Inx integral e to the power minus Inx into sec nx dx. Now, this is nothing but e to the power Inx integral. Let us apply the Euler's formula here. E to the power minus I theta is cos theta minus I sin theta. So, cos nx minus I sin nx into sec nx dx. Now, this is further, if you solve it, this gives you cos nx into sec nx is 1 minus I tan nx. Dx. Now, we can easily integrate this. This is equal to e to the power I nx integral dx is x minus I times the integral of tan nx is 1 over n ln sec nx, because ln sec nx, when you differentiate with respect to x, what you get is 1 over sec nx, then sec nx into tan nx into n. Okay, so we get this, this is what we get, and then we can write further this as e to the power I nx is cos nx plus I sin nx, and this is to be multiplied by. So, if I write ln 1 over cos x, then it will be minus ln cos x. So, x plus I by n ln cos x cos nx. Okay, so what we will get, and let us multiply this. This will be x cos nx x cos nx plus I times x sin nx and then I by n cos nx ln cos nx, and then my I square is minus 1. So, minus 1 over n minus 1 over n sin nx ln cos nx. So, this is what we get. Similarly, we can find the value of 1 over d plus in, 1 over d plus in operating on sec nx. If you obtain that in a similar manner, we will get so 1 over d plus in sec nx. If we get, we will simply have x cos nx minus ix sin nx and then minus I by n cos nx ln cos x nx, and then plus minus 1 by n sin nx ln cos nx. Okay. So then we from 1 over d minus in sec n x we have to subtract 1 over d plus in sec n x. If we do that and divide by 2 in, what do we get? So hence by px is 1 over 2 in. Now from this value we subtract this, so x cos nx will cancel, ix sin nx and ix sin nx will add up, 2 ix sin nx we will get, and then in cos nx ln cos nx and in cos nx ln cos nx will add up, so 2 in cos nx ln cos nx we get, and then this expression and this expression will cancel each other. So we divide by 2 in, so we get x sin nx divided by n, and then here we get cos nx. So hence the general solution of the differential equation d square by over dx square plus n square by e equal to sec nx we can write as by x equal to by cx plus by px, which is equal to a cos nx plus b sin nx plus x sin nx by n plus cos nx ln cos nx divided by n square. So this is the general solution of this differential equation. Yeah, now we are going to study how to find the particular integral when Rx is of these some special forms. So the first result that we are going to consider is the result when Rx is an exponential function. So suppose Rx is e to the power alpha x, where alpha is some real number, alpha can be any real or complex constant. So 1 over fd when operates on e to the power alpha x. Let us find the particular integral when Rx is e to the power alpha x. So 1 over fd e to the power alpha x gives you 1 over f alpha e to the power alpha x, provided f alpha is not equal to 0. We can make use of this formula to determine the particular integral when Rx is of the type e to the power alpha x. Now to prove this formula, we can see that when we differentiate e to the power alpha x with respect to x, what we get is alpha times e to the power alpha x. If we again differentiate this with respect to d, that is we find the second derivative of e to the power alpha x with respect to x, which is given by d square e to the power alpha x, we get alpha square e to the power alpha x. Now so fd when operates on e to the power alpha x gives you fd is d square plus ad plus b. So d square plus ad plus b when operates on e to the power alpha x, we get alpha square e to the power alpha x, then a times alpha e to the power alpha x, then b into e to the power alpha x. So we get alpha square plus a alpha plus b into e to the power alpha x. Now this alpha square plus alpha a alpha plus b can be written as f alpha. So we get f alpha into e to the power alpha x. Now so fd when operates on e to the power alpha x gives us, now let us suppose that f alpha is not equal to 0. So when f alpha is not equal to 0, let us first operate on both sides by the operator 1 over fd. Since 1 over fd and fd are inverse operators, we have left hand side as e to the power alpha x and the right hand side is 1 over fd operating on f alpha e to the power alpha x. Now f alpha is a non-zero algebraic multiplier. We have assumed f alpha to be non-zero. It is a non-zero algebraic multiplier. So this is same as f alpha times 1 over f d operating on e to the power alpha x. Now let us divide this equation by f alpha. So dividing we get 1 over f d operating on e to the power alpha x equal to e to the power alpha x over f alpha. So this is the proof, and this method fails when it happens that f alpha turns out to be 0. Let us apply this method to find the particular integral. In the case of the example, d square by over dx square plus by equal to e to the power x plus 1 whole square. So this differential equation can be written as d square plus 1 by equal to e to the power x plus 1 whole square. Let us first write the complementary function. So the auxiliary equation is m square plus 1 equal to 0, that is m equal to plus minus I. So complementary function by c x equal to a cos x plus b sin x. Let us find the particular integral y p x. This is given by 1 over f d. F d is d square plus 1 operating on r x. R x is e to the power x plus 1 whole square. Now this e to power r x is e to power x plus 1 whole square. So we have to square this and write now this is nothing but we operate by 1 over d square plus 1 on each of the terms of this bracketed expression. Okay. Now this is 1 over d square plus 1 e to the power 2x can be found from the formula 1 over f d e to the power alpha x equal to e to the power alpha x divided by f alpha, because here alpha is equal to 2, and when we replace dy in f d is d square plus 1, when we replace dy alpha there, it is f alpha is not equal to 0. So this is equal to 1 over 2 square plus 1 e to the power 2x. Now 2 is an algebraic multiplier. I can write it 2 times 1 over d square plus 1 operating on e to the power x. So alpha is 1 here. So I write 1 over 1 square plus 1 e to the power x, and here 1 can be regarded as e to the power 0x, e to the power 0x. So alpha can be taken as 0 and we can get the value of this. So this is equal to further 1 over 5 e to the power 2x, then 2 over 2, so e to the power x, and then alpha is 0 here, so 1 over 0 square plus 1, so plus 1. So then general solution is by x equal to by cx plus by px. Now let us go to short methods of finding 1 over f d sin cx and 1 over f d sin cos cx, where c is any real number. Now we are finding short methods for finding the result of operating by 1 over f d on sin cx or 1 over f d operating on cos cx. Now if n is a positive integer, notice that d square to the power n sin cx is equal to minus c square to the power n sin cx. Let us prove this. When we operate by c on sin cx, that is we differentiate sin cx with respect to x, we get c times cos cx. Let us again operate by d on this c cos cx. So, that is d square sin cx gives you d of c cos cx, which is equal to minus c square sin cx. I can write it as minus c square times sin cx. Now, d cube then sin cx will be minus c square into c cos cx, and d to the power 4 sin cx will be equal to minus c square into minus c square into cos cx, which can be written as minus c square square cos sin cx, sorry, sin cx. So, minus c square is square sin cx, and thus we can say that d square square sin cx is nothing but minus c square square sin cx. It can be by mathematical induction we can extend this to and so on. D square to the power n sin cx is equal to minus c square to the power n sin cx. Similarly, we can find d square to the power n cos cx. This will come out to be minus c square to the power n cos cx. Now, let us see, suppose fd, the expression of fd contains only even powers of d, and we denote it by phi d square. Then from here we can see that phi d square when x on sin cx, the effect of this operation of phi d square on sin cx will be phi minus c square sin cx, because here we see that whenever we operate by d square on sin cx, we get d square to the power n on sin cx, we get minus c square to the power n sin cx. So, phi d square when operates on sin cx, we will get phi minus c square sin cx. Now, so what we get is when phi d square operates on sin cx, we get phi minus a square sin cx. Now, let us assume that phi minus a square is non-zero, phi minus c square is non-zero. Then if we operate by 1 over phi d square on both sides, phi d square and 1 over phi d square are inverse to each other, we will get sin cx equal to 1 over phi d square phi minus c square is an algebraic multiplier, non-zero, we divide it by minus phi phi minus c square and get 1 over phi d square operating on sin cx equal to sin cx divided by phi minus c square. So, similarly we can show that 1 over phi d square when operates on cos cx, we get 1 over phi minus c square cos cx, provided phi minus c square is non-zero. More generally, if we have to operate by 1 over phi d square on sin cx plus d, where c and d are constants, then we get 1 over phi minus c square sin cx plus d. We can prove this rate in a similar manner. Now, let us take an example. Suppose we take the example 1. Example 1 can be written as d square minus 4d plus 1 operating on by equal to 2 cos 2x. We know how to find the complementary function, so I will discuss only particular integral. So, by px equal to 1 over f d, which is d square minus 4d plus 1 operating on 2 cos 2x. 2 is an algebraic multiplier, I can write it outside. Now a here, c here is 2, so we replace d square by minus c square. So 1 over minus 2 square, for d square we write, and minus 4d plus 1 we leave just like that, cos 2x. This is 2 times 1 over minus 4 plus 1, so we get minus 4d minus 3 cos 2x, and this is also equal to minus 2 times 1 over 4d plus 3 operating on. Now what we do is, to get the operation of 1 over 4d plus 3 operating on cos 2x, let us operate by 4d minus 3 on cos 2x and 1 over 4d minus cos 3. So minus 2 times we write 4d minus 3 and 1 over 4d minus 3. They are inverse of each other. So we get this. Now this will be equal to minus 2 in the denominator we have 16d square minus 9 cos 2x. Again replaced d square by minus a square, we shall have, so minus 2 times d square by minus a square, so 16 times minus 2 square minus 9 cos 2x. So this is minus 64 minus 9, so that is minus 73, so we get 2 by 73, and then 4d minus 3 operating on cos 2x. Now we have to operate by the operator 4d minus 3 on cos 2x, so we get 2 times 2 over 73, 4d cos 2x means derivative of cos 2x with respect to x, so minus 8 sin 2x minus 3 cos 2x. So this is the particular integral in this case. We add to this complementary function and write the general solution. Now in the case of example 2, d square plus 1 by equal to cos square x by 2, what we do is, to find the particular integral we shall write. Now let us find the particular integral in the case of example 2. So in the case of example 2, particular integral by px is equal to 1 over d square plus 1 cos square x by 2. Since this is cos square x by 2, we have to convert it to cosine x function to apply the formula that we have just now proved. So we shall write it as 1 over d square plus 1 plus cos x by 2, and this will be then by 2 1 over d square plus 1 operating on 1 plus cos x. So this will be 1 by 2, 1 over d square plus 1 operates on 1 can be regarded as e to power 0x. So we will get 1 over 0 square plus 1, and then 1 over d square plus 1 operates on cos x, we shall replace d square 1 by d square by minus 1 square plus 1. So which is not defined. So how we shall deal with this example we shall see in our lecture tomorrow, because here 1 over d square plus 1 becomes 0 when d square is replaced by minus a square. So this example we cannot find a particular integral like this. This will be found, this will be tackled in my lecture which I give tomorrow. Thanks.